Well, obviously, if we're going to study some properties, we're going to have to measure them. And here we get into all of that stuff related to measurement. And quickly, we have to talk a little bit about what we're up to and the scientific method you probably heard about in your previous science courses. And we're not going to spend a lot of time reviewing this scientific method. It is a view of the world in the sense that it relies upon the testing of hypotheses and the formulation of experiments in order to test those hypotheses. Observations are made both qualitatively and quantitatively, and we attempt then to organize the world in terms of models of individual sort of small systems, and then ultimately in terms of theories, which of course you remember are structured views of how the world works. You're going to, in this class, be repeating really a lot of classic experiments on matter and the changes that it goes through, and we will formulate hypotheses, although most of ours will be the same sort of hypotheses that the original chemists had when they tried these very experiments. And so all under the umbrella of this scientific method of explanation. You've probably been introduced before to the metric system. We're going to use the metric system and the SI, Scientific International System of Measurement. We're going to make quantitative observations about lots of properties, and obviously that quantitative observation requires that we have something that has size or magnitude that we can measure using some measurement tool. There are base units for this scientific international system for these various quantities. You can go out on the internet, as we'll show you in class, and corral a bunch of this information very, very quickly. And this entire chapter, this entire process is now much, much easier for you with the widespread availability of unit converters out there on the internet. You don't have to do this physically yourself, although it's critically important that you understand what you're up to when you do it. We're also, of course, because chemistry will measure things that are very, very small and numbers that are very, very large, are going to be using the scientific notation and the powers of 10, and we'll see that a number of those powers of 10 can be identified by prefixes, and we're going to have that in our everyday language, so you're going to have to understand how it works. We need to distinguish between the quantity itself, that property that we are measuring, and the unit that we are using to measure it. Perhaps the most easiest examples is the first one here, where we're talking about the property of mass. Mass could be measured in a whole variety of different ways by comparing the mass of an object to some other object. We have chosen to use then this unit, the gram or the kilogram, depending upon the amount of matter, to represent then that unit. Here are those 5 important base units in beginning chemistry. There are, in fact, 7 base units that we need to define all the other ones, but the other 2 here are not going to be critically important to us, so we're going to let them alone. Mass, length, time, amount, and temperature, and here then the units that we use in the SI system to represent those quantities. Abbreviation is going to be really important to us, and it's important that we all use the same abbreviations. Again, this idea of efficient and yet precise communication is critical in chemistry, and hence we're going to use all the correct element symbols correctly rendered, as well the correct units and the correct abbreviations for them. Most of these are probably easy enough for you to use. The only one where we'll mix and match is the mole, which we'll get into later. We'll oftentimes use MOL as a shorthand version of it when we want to be clear in our communication. Whenever it appears in formulas, though, it will be represented by the symbol M. Notice that this K is big, it's a big K, and that the Kelvin is a measure of our temperature. S for second, M for meters, good to go. In the olden days, students had to sort of memorize these various prefixes and what they represented. You can, of course, using your laptop, go out and get and find one of these tables and have it available to you at a moment's notice, and so this is a lesser important task. Now, perhaps the most familiar prefixes are those that are right around the base unit, kilo, centi, and milli, you probably are aware of. The base unit represents then whatever it might be, gram. And then as we go up in size, kilogram, megagram, notice that our powers of 10 jump by 3 orders of magnitude. And here we have then obviously then a kilogram represents 1,000 grams. a megagram, a million grams. We also in chemistry measure things that are very, very small. So as we go down, notice that we stick with our sort of powers of orders of magnitude 3 there, except for centi, which is a very convenient unit for the measurement of length, especially the centimeter. But milli, micro, and nano refer to increasingly smaller and smaller units, so that one, if you want to think about it that way, gram would be essentially 1 times 10 to the 9 nanograms, or 1 nanogram, 0.000000001 grams, 1 times 10 to the minus 9. We'll also be dealing with a whole bunch of derived units, and all this means is that we use our base units in order to get new units. For example, volume is a derived unit because it is length cubed, right? Length times width times height, but all of those are length measurements. We can measure in a variety of units, and we'll see that some of these units are most convenient for liquids and others of them are most convenient for solids. Density, as I said before, an intensive physical property, hugely important to us, is a measure of mass per unit volume. And whether we use grams and meters or grams and centimeters, we still end up with a good intensive property measurement and derived from mass and length. Velocity, another example of a derived measurement. We really don't deal with velocity much in chemistry, but here length divided by time. And concentration, which is going to be hugely important to us later in the class, is a measure of the amount of substance, moles, divided by the volume, in this case in liters. So we'll use these derived units all the time. We'll have to convert from one unit to the next, and although this process is enormously simplified for you using your laptop and widely available unit converters, it's important to understand what's going on here, because I can't stress how critical having the right units is. I'll say it 100 times, units, units, units. Every time you do any kind of quantitative problem, I'll jump up and down and say units, units, units. You must include units with your answer. And the units can often provide you with a clue as to whether or not you've done the problem right. Here, for example, we're trying to convert kilograms into grams, and we do so formally, of course, by constructing this conversion factor that shows the relationship between the two units. You might be familiar enough with this conversion already to be able to just move the decimal point. That's one of the benefits of using that metric system and the scientific international units. But in this case, we're demonstrating the concept, and so let's walk through it really quickly. Here's our original number in kilograms. Here is our conversion factor that allows us to move between the two, and here, of course, is our answer. Notice that if I take 3.24 kilograms and multiply by 1,000 grams per kilogram, that the kilograms over the kilograms cancel, just like it were a number, and we're left with our answer in the numerator units, grams here. The two properties then of that conversion factor, and these are critical, must be equal to 1. That is to say, 1,000 grams and 1 kilogram have to be the same. And notice that it has to be arranged in order for the correct units to emerge. For example, if I were to take this conversion factor and flip it, now I would have kilograms over grams. And now when I multiply through, my answer would have the units of kilograms squared per gram, which is nonsensical, which tells us then, of course, we did not do the problem correctly. You'll do some practice with this a lot. In fact, we'll do one right now. It's sometimes useful to go through multiple steps in order to get to where you need to go through that base unit. Here an example of centimeters to kilometers. Well, I don't know, I don't remember how many centimeters there are in a kilometer. There are a lot. But I do know the relationship between centimeters and meters and kilometers, and so I can handle the problem in 2 steps. It's handled just like you might imagine. 2.34 e to the 10. I'll use this shorthand e a lot just because it saves me writing times 10 to the 10 centimeters. I know that there are 100 centimeters in 1 meter, and I know that there are 1,000 meters in 1 kilometer. And now if I do my unit analysis, centimeters over centimeters, meters over meters, gives me indeed my units in kilometers. And all I have to do is take the 2 times 3.34 times 10 to the 10 and divide by 100 and then divide by 1,000 and get the correct answer. In this instance, of course, all I really have to do is move the decimal point 1, 2, 3, 4, 5 places to the left, which of course means subtracting 5 from the exponent, and the answer of course would be 2.34 times 10 to the 5. By virtue of that conversion. Again, you have unit converters, and I'll go ahead and let you use them, but it's important that you understand exactly what's going on. We also have special conversion factors that are needed to go between measurement systems. This is an example of one of those. It's handled no differently than any other. You have that unit converter in your on your laptop that easily can do these problems. We won't be going between systems, metric system to English system, and so we won't have to face any of these problems, but it's easy enough to do. All you have to do is set it up the same way, 3.82 meters. Obviously here I want to make my meters into feet. I want my feet to emerge. So feet go on the top, meters go on the bottom. I just plug in these numbers, 3.281 to 1. And then notice that unit analysis, meters over meters, gives me the feet that I need. And now it simply takes my 3.82, multiplied by 3.281, and have my answer. So measurement and scientific method, metric system, all key to us, and we'll use them throughout the course.